Hi everyone. In lesson 7, we introduced the average or the arithmetic mean. In lesson 8, we're going to extend this idea to estimating a mean from a frequency table, and we're going to talk about weighted means. What if some values count more than others? Okay, so let's begin by estimating a mean from a frequency table. And we're going to go back to our frequency table for the president's ages. Remember, there were 2 presidents who became president in their early 40s. There were 7 presidents who became president in their late 40s, and so forth. And we obtained that from the original raw data set over here with the 45 presidents' ages. But this list of 45 ages was a bit of a mess. So it was easier to picture the data and picture their distribution by writing out the frequency table. But now let's say that we want to estimate the mean age, the average age. And let's say that we don't want to take all 45 of these ages, add them up and divide by 45. Maybe we don't have time for that. We don't have Excel available. Or maybe we've lost the original data set and we're left with this frequency table. So if we just have the frequency table, how can we estimate the mean if we've lost the original data and we just have the frequency table? So just based on the frequency table alone, how could we estimate the average age of a president? I'm becoming president. Okay, so some ideas here. So basically, these various ages are being binned. They're being placed into classes. So for example, if we look over here, we have the data in a more granular form. They're kind of grainy. So we had 7 presidents who were in their early 60s, okay? Now here's the thing. Given that we had 7 presidents in their early 60s, when we estimate the sum and then the average, how could we treat these 7 ages? Could we, for example, estimate that they were all 60 years old on becoming president, taking the lower class limit? Well, that might not be wise because that might have the effect of biasing our estimates to the low end. On the other hand, if we use 64 as a common age, if we assume that all 7 presidents here were 64 years old when they became president, then we would be biasing the data on the high end. If we take the upper class limit, it's likely that we'll be obtaining overestimates for the sum and then the average. So instead of taking the lower limit, 60, or the upper limit, 64, what might be more reasonable? How about the average of the lower and the upper class limits? The average, like the midpoint. How about 62 years? Let's assume that these 7 ages here were all exactly 62 years, or perhaps more believably, let's assume that the 7 ages averaged to 62 years. That might be more believable, that the 7 ages on average, they average out to 62 years. So once again, what's the idea here? The age class, 60 to 64 years, has as its class limits 60 years and 64 years. The problem is that we'd be in danger of performing underestimates if we take the 60 years, and we're in danger of performing overestimates if we take the 64 years, the lowest and highest values in the class. So instead, we're going to use the class mark for this class, which is the average of the class limits, the midpoint of the class. So for the age class, 60 to 64 years, the class mark would be the average. Again, how do you take the average of 2 numbers, these class limits? You add them up and divide by 2. We get 62 years. For simplicity, we're going to assume that all 7 presidents' ages in this class were all 62 years old. All 62 years old. Now again, if this assumption seems too strange to you, we'll get the same results for the estimated sum and average if we assume that the 7 presidents' ages averaged 62 years. Again, that's likely to be more believable to you. And the benefit of using 62 years as opposed to 60 or 64 years is that This scheme will not automatically bias our estimated mean towards either the low end or the high end. We're aiming for an unbiased estimate. Okay, so now let's take a look at these classes and now their class marks. So for the age class 35 to 39 years, we're going to use 37 years as our class mark. Granted, that turns out to be irrelevant because we had 0 ages in this class anyway. For the age class 40 to 44 years, we use 42 years, the class mark. That's the average between 40 and 44. There were 2 ages in this class. 45 to 49, we use 47 years, the average of 45 and 49, and so forth. 50 to 54, we use 52. 55 to 59, we use 57. As I just mentioned, 60 to 64, we use 62. 65 to 69, we use 67. And 70 to 74, we use 72. Remember, each of our age classes have equal width. That's why I have 70 to 74 here. Okay, so again, we're going to assume that there were 2 presidents' ages that averaged 42 years. There were 7 presidents' ages that averaged 47 years, and so forth. Okay, now using these class marks and these frequencies, we're going to estimate the sum of the 45 ages and then find an estimate for the average of the 45 ages. By the way, remember that these frequencies have to add up to the population size, capital N or 45. The frequencies are values for F. The summation of the frequencies better be capital N, the population size. These better add up to 45. We're making sure that our table is accurate. It's a check. Okay, so how do we go about estimating the sum of the 45 ages using these class marks and these corresponding frequencies? Okay, well, there were no ages in this lowest class. There were 2 ages in this next class. Again, we're assuming that these 2 ages were 42 years, or they averaged to 42 years. And then these 7 ages, we're assuming, these 7 ages here, we're assuming averaged to 47 years, or more simply, they were 47 years. We're assuming these 7 ages were 47 years. Whether you think of the 7 ages as being exactly 47 years or just averaging to 47 years, we're going to end up with the same result, and so forth. So if we do that, here's what we get. A long way to estimate the sum would be to add copies of the various class marks. So again, we're assuming that there were 2 copies of 42 years. So what would be the contribution to the estimated sum? It would be 42 plus 42 in blue here. There were 7 ages in this class. We're assuming that all 7 ages were 47 years old, or they averaged to 47 years old. Either way, we would take the sum within this class to be the following. We would take the 7 copies of 47 here and add them up. And that would be the contribution to the sum of the 45 ages. Okay, and then there were 13 ages we're assuming were 52 years or averaged to 52 years. So we take 13 copies of 52, add those up, and so forth. So then, by the time we're done with this, right, we end up with this huge sum here, this huge sum, which turns out to be 2,480 years. Bear in mind, there's only 1 age in the highest class, and the class mark was 72. We only had 1 copy of the 72. Now, again, when you add all these up, our estimated sum would be 2,480 years. Just for kicks, if we were to go back to the original data values, these here, what would be the sum? Let's ask Excel. I have the actual ages here, the raw data. Let's ask Excel. The actual sum, B2 to B46. Again, we're rounding down ages to the year, right? Look, our estimate for this, okay, so the actual sum based on our Excel spreadsheet was 2,475 years, and our estimate was 2,480 years. That's pretty close. Now, hold on. You might be asking, but this is so much adding. I may as well just go back to the original data set and add these all up. How can we make this much more efficient? How can we make this much more efficient? For example, the 7 copies of 47. The 7 copies of 47. What's a fast way of computing this sum here? Taking the 47 copies of 47 and adding them up. Instead of adding them up directly, what could we do? We could just take 47 times 7, or vice versa, 7 times 47. And we can do that for each of these classes. So for example, in this second class here, we can estimate the sum of the ages by 2 times 42. 42 plus 42. For this third class here, we can estimate the sum of the ages in this third class by taking 7 times 47. And so forth. So here would be a much faster way of doing it. We're using the fact that repeated addition can be represented with multiplication. Here's a much faster way to get the estimated sum. For each class, multiply each class mark, the x value, by the class frequency, the f value, to get the class sum, f times x. These are values of f times x, 2 times 42, 7 times 47, and so forth. And these class sums would be the sums of the ages in the class. So this here would be the estimate for the sum of ages in this third class. Right. So then we would get this. The computation arises from a zigzag. And we see these zigzags a lot in our statistics class. So how do we get our estimated sum? We do 0 times 37, well, that's 0 anyway, okay, plus 2 times 42, that's 84. That's our estimate for the sum of the ages in the second class, 2 times 42, plus 7 times 47, plus 13 times 52, plus this times this, plus this times this, plus this times this, plus this times this. And then you'll get our estimated sum. All right. So by doing this zigzag, we obtain an estimated sum, again, of 2,480 years. The exact same result as if we had done it this way. So the zigzag method that you see over here is just a much faster and more efficient way of performing this grand addition over here, where we're treating repeated additions as multiplication problems. So here we have 7 times 47 instead of adding all this stuff up. All right. Now, again, folks, how do we take an average? We take our sum, or estimated sum, and divide by the population size, capital N, the sum of the frequencies, 45 here. There are 45 ages. So we now divide the estimated sum by the number of ages, the population size, to get our estimated mean. Here's our formula. The estimated mean is given by the estimated sum divided by N. The population size, the number of values, 45. 45 was the population size, capital N. So using professional notation, don't get a nosebleed here. On the top, how do we get our estimate for the sum? It was from that zigzag. And we often denote zigzags by summation something times something, right? Summation f times x plus f times x plus f times x plus f times x, and so forth. Technically, we'd have subscripts. It would be f sub 1 times x sub 1 plus f sub 2 times x sub 2, and so forth. But we're not going to get that detailed. We're adding products. It's this times this plus this times this plus this times this, and so forth. Summation f times x, that's the zigzag. And you can go either way. You could also go the other way. You can go 37 times 0 plus 42 times 2. It doesn't matter. Okay? And in fact, you could reverse the order. Both multiplication and addition are commutative. There are various orders you can perform these in. For example, you could switch these guys, or you could reverse the order. That's fine too, of the sum. All right. Anyway, our estimated sum was 2,480. All right, from the zigzag. Okay. So from the zigzag in green, that was 2,480 over here. That was that zigzag guy up here. Over 45, and we get to the nearest tenth of a year. Remember, we go one decimal place further. We get about 55.1 years, our unit. So our estimated mean for the present ages was about 55.1 years. In fact, if you go to our Excel spreadsheet, what was the average? The mean. The actual mean was equals average, B2 to B46, hey, 55.0. For all practical purposes, we got it. Because remember, when we entered these various ages, these were already rounded down, right? There was already a lot of rounding going on here, right? I mean, someone who was 47 years and 11 months, we round down to 47. There was already a bunch of rounding going here by months, right? So, I mean, 51.1 years versus 55.0 years from our Excel spreadsheet. For all we know, maybe 55.1 years was more accurate if you throw in months and days. In any case, I think we did a great job. Okay, this really matches up with our Excel spreadsheet, right? Excel says 55, we got 55.1. Come on, with months and days, we might have been more accurate this way. All right, estimating means from a frequency table. Next up, weighted means, including your GPA. Next time.